Welcome to Understand the Math. Sometimes when we evaluate limits, we get an expression that doesn't immediately tell us what the value of the limit is. This expression is called an indeterminate form. Let's now learn how to evaluate limits with these forms. Limits of the form 0 divided by 0 or infinity minus infinity are called indeterminate forms. These indeterminate forms can equal 0, plus or minus infinity, or they can equal a finite number. Let's look at an example of a limit with an indeterminate form so that we can better understand this. We're going to evaluate the limit as x approaches 2 of x squared plus x minus 6, all divided by x minus 2. The first thing that you want to do when you evaluate limits is do direct substitution and just plug in the value. This gives us 2 squared plus 2 minus 6, all divided by 2 minus 2. Up top, we have a 4 minus 4, and in the denominator, we have a 0. So this gives us 0 divided by 0. And that's what we call an indeterminate form. To find out what this limit equals, we can look at its graph. The blue line is the graph of x squared plus x minus 6, all divided by x minus 2. To evaluate the limit of this function at x is equal to 2, we look at our graph and look at the limit from the left and the limit from the right, and we can see that that limit is going to equal 5. So we can say that the limit, as x goes to 2, x squared plus x minus 6, all divided by x minus 2, is equal to 5. And that's our answer. Notice that there is an open circle at x is equal to 2 because the function is not defined there. It was really nice to see the graph of this function to understand what an indeterminate form looks like graphically. But in practice, it's really nice to be able to evaluate this type of limit algebraically. Let's go ahead and let's do that. We have the limit as x goes to 2 of x squared plus x minus 6, all divided by x minus 2. Notice that our numerator is a quadratic, and we can factor that. So we're going to write this as the limit as x goes to 2. Factoring the top, we can have an x plus 3 and an x minus 2. And we all divide that by x minus 2. You can see that these two terms cancel, and this gives us the limit as x goes to 2 of x plus 3. And now we can just plug in what x is, and we get 2 plus 3 is equal to 5. And that agrees with the answer that we got from looking at the graph. In this last example, we use the algebraic technique of factoring to evaluate the limit. There are other algebraic techniques that we can also use, and we're going to look at those. An indeterminate form such as 0 divided by 0 or infinity minus infinity can be evaluated using one of these 5 techniques. The first one is factoring, and then we have multiplying by a conjugate, getting a common denominator, multiplying out a polynomial, or applying a piecewise function definition of an absolute value function. We're going to do an example of all 5 of these. We're going to look at 5 limit examples, and each of these uses a different algebraic technique to evaluate it. Let's look at our first example. The first thing that we always want to do is to just plug in our number and see what we get. So this is 25 minus 5 from the right squared, which is 25, all divided by 5 to the right squared again, so that's 25, minus 10 times 5, which is 50, plus 25. So you can see that this gives us 0 divided by 0, which is an indeterminate form. When we look at this problem, we see that we have a quadratic in the numerator and in the denominator. So that clues us in that we can probably use factoring to evaluate this limit. We will factor the top and then factor the bottom. So we have the limit as x goes to 5 from the right. Factoring the top, we get a 5 minus x and a 5 plus x. Now we can factor the denominator. This is going to be x minus 5 times x minus 5. Let's focus on this term and this term. Those terms are almost the same. They are just different by a negative. So what we can do is we can rewrite the term on the top and take a negative out. Let's write this as the limit as x approaches 5 from the right of minus x minus 5, and then we have a 5 plus x, and then our denominator is the same, x minus 5 and x minus 5. Now let's focus again on these two terms. They are the same now, so we can cancel them out, and we can now go ahead and substitute in that x is going to 5 from the right. This gives us a minus 5 plus 5 from the right, all divided by 5 from the right minus 5. On the top, we have a minus 10, and then in the denominator, we can think of 5 from the right as 5.000, lots of zeros and then a 1, minus 5. So this is a number close to 0, but it's going to be positive. So we have a negative number divided by a really small number that's positive, and that's going to give us an answer of minus infinity. So our limit is equal to minus infinity. Let's now look at our second example. We're going to begin by substituting in that h is equal to 0. This gives us the square root of 1 minus 1, all divided by 0. So we get 0 divided by 0, which we saw up above, is an indeterminate form. Often, when we have a limit with a square root, we can evaluate it by multiplying by a conjugate. Let me remind you what a conjugate is. The conjugate of the square root of x minus a is equal to the square root of x plus a. When we multiply it by a conjugate, often terms will cancel out. So that's why we're going to do this. We're going to take the limit as h goes to 0 of the square root of 1 plus h minus 1, all divided by h, and we're going to multiply it by the conjugate. The conjugate is going to be the square root of 1 plus h plus 1. All we're doing is changing this sign. And then we can't change the problem, so whatever we multiply on the top, we have to multiply on the bottom because we can really just be multiplying by 1. Otherwise, we would change the problem. Now let's go ahead and multiply this out. This is the limit as h goes to 0. Let's use the FOIL method and multiply the first terms. So that's root 1 plus h times root 1 plus h. So that gives us a 1 plus h. Now let's multiply the outer terms. So we're multiplying square root of 1 plus h plus 1. So that gives us square root of 1 plus h. Now we're going to multiply the inner terms, and that gives us a minus square root of 1 plus h. And then lastly, we'll multiply the last terms, and that's going to give us a minus 1. And our denominator looks like h times the square root 1 plus h plus 1. Notice that I did not multiply out the denominator. It's always good to hold off not multiplying out the term that doesn't have the two conjugates in it. Now let's see what cancels. This term is going to cancel with this term, and our 1 is going to cancel with our 1. So we have the limit as h goes to 0 of just h on top, and then we have an h in the denominator and a square root of 1 plus h plus 1. Now you can see that our h's cancel, and that's why I didn't multiply things out. And we can now just go ahead and plug in h as 0. We have a 1 on the top. That comes from our h canceling. And then we have the square root of 1 plus 0 plus 1. So this just gives us an answer of 1 divided by 2. And that's what our limit is equal to. Let's now look at our third example. We'll start by substituting in what x is. This gives us 1 all divided by 0 times the square root of 1 minus 1 over 0. This gives us 1 over 0 minus 1 over 0, and that's infinity minus infinity. And just like 0 divided by 0, this is also in indeterminate form. When you have a limit that equals infinity minus infinity, it comes from having two terms, and we can often evaluate a limit like that by combining the two terms and getting a common denominator. So let's go ahead and let's do that. We're going to get a common denominator equal to x times the square root of 1 plus x. We have the limit as x goes to 0. Let's write our denominator first. We have x square root 1 plus x. On the left, we have a 1. And for our term on the right, we only have an x. So we need a square root of 1 plus x. So we're going to subtract square root 1 plus x. Now let's go ahead and plug in x is equal to 0. So we have 1 minus the square root of 1 on the top, and we have 0 times the square root of 1 on the bottom, and that gives us 0 divided by 0, which is our indeterminate form that we looked at for our first and second examples. Notice now that we have a term in the top that's a number minus a square root. That means that we can multiply by a conjugate. Let's go ahead and let's do that. This is the limit as x goes to 0, 1 minus the square root of 1 plus x, all divided by x square root of 1 plus x, and let's multiply by the conjugate, 1 plus square root of 1 plus x, all divided by 1 plus square root of 1 plus x. If I were teaching this in class right now, I would start to get a lot of moans. I know this is a long problem, but hang with me. You can do this. Let's multiply out our top. We'll use the FOIL method. We'll multiply the first, which is 1. We'll multiply the outer terms, which gives us a plus square root 1 plus x. We'll multiply the inner terms, which is minus square root of 1 plus x. And then the last terms, which gives us a minus, and then the square roots combine to be a 1 plus x. And then our denominator, we just have to copy down x square root 1 plus x. Do not multiply the denominator out because we're hoping that terms are going to cancel. Let's look back up at our numerator and we'll cross out the terms that cancel. We have this term and this term cancel, and then our 1's cancel. So let's go ahead and rewrite this as the limit as x goes to 0. We have a minus x up top, and then down below we have an x square root of 1 plus x, 1 plus square root 1 plus x. Our x's cancel, which is why we did not multiply out the denominator. And now we can go ahead and plug in x is 0. So up top, we get a minus 1. And then in our denominator, we have square root of 1. And then we have a 1 plus square root of 1. So this is minus 1 all divided by 2. And that's the value of our limit. Remember that in this example, we used two techniques. We got a common denominator, and then we multiplied by a conjugate. Let's look at our fourth example. This one isn't as bad as our third one. Let's start by plugging in h is equal to 0. This gives us a 2 plus 0 cubed minus 8, all divided by 0. So this is 8 minus 8 over 0, which is 0 over 0, which is an indeterminate form. Notice in this problem that we have 2 plus h raised to the third power. Whenever you have a limit with an expression raised to a power, you can often evaluate it by multiplying out that power and then hoping that some terms cancel. We're going to begin by multiplying out 2 plus h cubed. You may not remember that formula, so let me go ahead and let's write it down. A plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. If you don't want to remember that formula, you can just multiply 2 plus h cubed out by hand. I'm going to use the formula, so I'm going to write down this is the limit as h goes to 0, 2 cubed plus 3 times 2 squared times h plus 3 times 2 times h squared plus h cubed. And then we can't forget we have a minus 8 to tag on there. All of this gets divided by h. Now let's go ahead and let's simplify. This is the limit as h goes to 0. We have an 8 plus 4 times 3 is 12, so we have a 12h plus 6h squared plus h cubed minus 8, all divided by h. Now let's look at our terms that cancel. We have an 8 that cancels, so that's great. Notice in the numerator that we have an h common to every term. So I am going to factor out an h, and we'll write this as the limit as h goes to 0. We'll pull out an h, and we have a 12 plus 6h plus h squared, all divided by h. Now you can see that our h's cancel, and we can just go ahead and substitute in that h is going to 0. This gives us 12 plus 0 plus 0, so our limit is equal to 12. Let's now look at our last limit example. This is equal to the absolute value of minus 4 plus 4, all divided by minus 4 plus 4. So this is the absolute value of 0 divided by 0, and we end up with our indeterminate form 0 divided by 0. Notice in this limit that we have an absolute value function. Whenever you have a limit with an absolute value function, the best thing to do to evaluate it is to break up that absolute value function into pieces. Just as a review, the absolute value of x is equal to positive x when x is greater than or equal to 0 and minus x when x is less than 0. We're going to use this as a model to find out what the absolute value of x plus 4 is equal to. It's just going to be equal to x plus 4 when x plus 4 is greater than or equal to 0, and then minus x plus 4 when x plus 4 is less than 0. Let's now see what this piece is equal to. Let's bring the 4 to the right. So this is just x is greater than or equal to minus 4, and then this piece is x is less than minus 4. I'm going to highlight these because we're going to need that. We're going to break up this limit into our left-hand piece and then our right-hand piece. Let's look at the limit as x approaches -4 from the left. That's going to be this piece right here because x is less than -4. So we're going to substitute in for our numerator minus the quantity x plus 4. So we have a minus x plus 4 on top. And then down below, we have an x plus 4. These terms cancel. So we're left with a value of -1. Now let's look at our right-hand piece. This is the limit as x goes to -4 from the right. We're going to plug in x plus 4. So we have an x plus 4 on the top, x plus 4 on the bottom, and we end up with a value of 1. Notice that our limit from the left does not equal our limit from the right. We know from the definition of a limit that it's only going to exist if the limit from the left equals the limit from the right. So we can conclude that the limit as x goes to -4 of absolute value x plus 4 all divided by x plus 4 does not exist. So we're going to write this as DNE for our answer.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.